Here we go. In section 8.3, we're going to take a look at graphing rational functions. So with a rational function, we're looking at something, so some f of x, where we have a numerator that's a polynomial and a denominator that is also a polynomial. And we often refer to these as p of x and q of x. And I don't know why they chose those variables, but they do. Mathematicians and textbook writers, they call them p and q. All right, so our rational function might be continuous, which means there's no jumps, no breaks, no holes. Essentially, there's no values that make the denominator equal to 0. That's kind of the key right there. In fact, I'm going to highlight it. It's so important. No values that make the denominator equal to 0. Now, maybe we will have a rational function that is discontinuous, and if it's discontinuous, we're going to have two different situations, maybe one or maybe both. We might have infinite discontinuity. So this is an example of something that represents infinite discontinuity. As you can see, these curves seem to be approaching some asymptote and heading off toward infinity, maybe up toward infinity or down toward infinity, depending on what the branches of this rational function look like. So if you have an infinite discontinuity, we call that a non-removable discontinuity, and you'll see why here in a minute. Maybe we have a removable discontinuity. Removable discontinuity is also called point discontinuity. What happens is you're going along, and then there's a hole, and then you keep going, like so. So that's called removable discontinuity, or sometimes called point discontinuity, because it's like they've just removed one point on the graph. In pre-calc, we'll take a look at jump discontinuity. And jump discontinuity is where, you're going, and then you have a hole, and then your graph jumps up, and then keeps going like so. This is called jump discontinuity, but we're not going to work with that in Algebra 2. Okay, so we've got two main kinds of discontinuity, removable and non-removable. So let's take a look at some examples. In our first example, let's take a look at the rational function y equals x plus 3 over x squared minus 4x plus 3. So remember factoring? Oh yes, I love to factor. I'm so glad you mentioned it. I haven't factored in forever. I've just been dying to factor. Well good, today is your lucky day. X squared minus 4x plus 3, what would that factor into? It's going to factor into -1 and -3. Remember, we're looking for two numbers that multiply to 3 but would add up to -4. Ah, yes, good old factoring. So this is going to factor, like I said, into x minus 1 and x minus 3. I'm just going to cross that out because now I've replaced it with its factors. And nothing cancels. So in other words, I can't cancel the x plus 3 and x minus 3. Those aren't the same. But what I do have are two vertical asymptotes. I'm going to have vertical asymptotes at x equals 3 and x equals 1. So these three little dots that I'm drawing right now, those three dots are the word therefore. So I've done some math here, I've made a statement, and then I can say therefore this function has non-removable discontinuity, at x equals 3 and x equals 1. Done. That's all I wanted to say about that. Tomorrow we're going to take a look at graphing, or in our next video we'll graph. But today we're just identifying the locations and the types of discontinuity. So, example A, done. Let's take a look at another example. So here we have y equals 5 over x squared plus 1. Okay, so x squared plus 1. It doesn't factor. It's not the difference of two squares. I don't know. Let's see. If I went x squared is equal to -1, like if I set it equal to 0, I would take the square root, and I take the square root, and I'd have x is equal to plus or minus I, which is non-real. So, whatever. That was pointless. So, what I can say here, I wasn't able to factor. I wasn't able to cancel anything out. This function is continuous. This function will be continuous because there are no values of x that make the denominator equal to 0. Because there are no values of x that make, something over 0. This is the word make. It doesn't look like an M, does it? Okay, that's all I have to say about letter B. There's nothing I can plug in there to make that become a 0. Okay, then let's go on to letter C. Example C, and then this will be it, so stay with me. We've got x squared minus 3x minus 4 over x minus 4. X minus 4. Hey, another opportunity to factor. Yes, I'm so excited. Can you tell me two numbers that would multiply to negative 3, but multiply to negative 4, but add up to negative 3? How about negative 4 and positive 1? So x minus 4, x plus 1. Okay, I like that. So what I see here, this is an interesting situation. I have these x minus 4s. These x minus 4s technically cancel out. So x equals positive 4 is a point of discontinuity because I canceled out x minus 4. I don't know, because I canceled out those x minus 4s. All right, x minus 4 cancels out. So x equals 4 is going to be a whole. I didn't say that very clearly. I've kind of got distracted here. So let's go with our little 3 dots that stand for the word therefore. So therefore, we have removable. Remember, removable is sometimes called point discontinuity. We have removable or point discontinuity at x equals 4 because x minus 4 over x minus 4 cancels. And that's all I have to say about that one. I'm going to go back up here in your notes, and I'd like you to do that too. Go back up here to where it said removable discontinuity, or non-removable, I mean. Remember that non-removable also is known as infinite. That's where you're going to be having some asymptotes. Okay, so that's all I have to say about that. If you want to go back and re-watch anything, now's the time. More practice tomorrow.